Hello, welcome. Welcome to a short discussion on Diophantine equation in number theory. What's meant by a Diophantine equation? If an equation which contains variables is to be solved for integer values, can be called a Diophantine equation. For example, the equation y square equals x cube plus k, where k is some integer constant. In this equation there are two variables, x and y. If you try to obtain the solution of the equation where both x and y are integers, if there exists such a solution, x and y, if that's both x and y are integer values, then we in general we call that kind of equations as Diophantine equation. We have a theorem. We have to discuss a theorem in which we will discuss the nature of the solution or the existence of solution of the example that is given here, y square equals x cube plus k. That equation, that Diophantine equation, y square equals x cube plus k, has no solution if k has the form, if the integer k has the form for n minus 1 cube minus 4m square, where n and n are integers, where m and n are integers such that the prime number p is congruent to, such that no prime number p congruent to minus 1 mod 4 divide m. Here we express the number, the integer k which is present in that equation in terms of the two integers m and n, for m and that is k equal to 4n minus 1 cube minus 4m square, and one of the integers m, that is m satisfies the m additionally satisfies the condition that p, where p which is congruent to minus 1, p congruent to minus 1, the prime number p congruent to minus 1 mod 4 divide m. Where it satisfies the condition that there exists no prime number p which is congruent to minus 1 mod 4 divides the number m. So these are the situation. Okay, then we want to prove the we are now going to prove the this result. So we want to show that if k has this form which is specified here, then that equation has no solution. For that let's assume for the time being the equation has a solution x and y. We assume that the equation has a solution x and y such that where both x and y are integers or integer solutions. We assume that the solution, that the equation has integer solution, that is there exists integers x and y such that the equation is satisfied. Since since k is congruent to minus 1 mod 4, okay, our finally we will show that if this assumption is true, then by proceeding using this assumption or this loose assumption, we will finally develop a contradiction. Okay, but in between we will make some claims based on we will make occasionally we will make claims on some other points, and we will develop in some cases we will develop contradictions in between the before coming to the end of the proof. We will do that in some occasions, but finally we have to show we have to develop a contradiction. But you can see that according to the condition given here, or the nature of the number k given here, when you expand this, you can expand this expression for k, and you can see that k is congruent to, after verifying the expanded form of k, you can see that k is congruent to minus 1 mod 4. So that is so this is a fact that can be verified, and that means k plus 1 is congruent to 0 mod 4. K is congruent to minus 1 mod 4 means k plus 1 is congruent to 0 mod 4. So in order to verify this, you can take this expression and you can expand it and the expression in the full form, in the expanded form, then that tells us that k is congruent to minus 1 mod 4. And since we have it is given that y square is congruent, since it is given, the equation itself tells us that y square is equal to x cube plus k, and therefore by transferring the right hand side terms to the left side, we get that y square minus x cube plus k is congruent to 0 mod 4. Okay, and now we represent this equation by 1, or that this step is given the number 1, and next step is given number 2. So adding 1 and 2, now we add the steps 1 and 2, we get the new expression that k plus 1 plus y square minus x cube plus k is congruent to 0 mod 4. Then here in this expression you can cancel k. In the one cancellation is possible. After that we get y square minus x cube plus 1 is congruent to 0 mod 4. Then you can write it as y square is congruent to x cube minus 1 mod 4, and we now claim that see, using this we can we claim that y square is congruent to 0 or 1 mod 4. We claim that based on this. Now we make the claim. Here we make the claim after deriving this step. After arriving at this step, we make the claim that y square is congruent to 0. Either y square is congruent to 0 or y square is congruent to 1 mod 4. How can we do that? If y is even, no? Okay. Okay, and this is okay, there's a mistake in my claim, but and this is not, we are our claim is not based on the previous expression y square is congruent to x cube minus 1 mod 4. No, and this is a new step. Actually we are now starting here a new step. Independently we start this step. Here we make the claim that y square is congruent to 0 or 1 mod 4. It's because we know that we are trying to obtain integer solutions for the equation, so y must be integer. Therefore any integer that you take, and after that after taking any integer, if you find the square, by squaring any integer, we want to show that whatever integer you take and square it, you can either show that it is congruent to 0 or congruent to 1 mod 4. For doing that, let's assume that y is let's think that y is even. Suppose y is even, and then y square will be then clearly y square is congruent to 0 mod 4. Next situation is y is odd. If y is odd, then if y is odd, then you can write that y is equal to 2k. You can write y in the form y equal to 2k plus 1, right? Where k is some integer, and y equal to 2 into k plus 1, where k is some integer. Then squaring that, we get that 2 into k plus 1 okay, yeah, 2 into k plus 1 the whole square, right? And actually that is not that step is not given here, but you can additionally you can do that. 2 into k plus 1 the whole square, that equal to 4k square. First term will be, when we write the expansion, first term is 4k square plus second term is 2 into 2k, 2 into 2k, okay, that's 4k, plus last term is 1 square, and therefore y square will be congruent to 1 mod 4 when y is odd. If y is odd, then y square is congruent to 1 mod 4. So this is independent. This claim is independent. It is not based on the previous step that we have derived here. Okay. Next, if y is an even number, think about that. Think about y is an even number. If y is an even number, okay, that the derivation is shown here. Then y square is congruent. Y square is equal to 4n square. Implies that y square is congruent to 0. So this is the way we it is explained here. The first case is proved here, but the second case is not. The steps for that second case is not written. And next we shall show that if x is even, or if x is even, or x is congruent to minus 1 mod 4, then y square is congruent to x cube minus 1 mod 4 cannot be satisfied. Okay, cannot be true. Then next we are going to, our aim is to show that if x is even, we shall show that if x is even, or if x is congruent to minus 1 mod 4. If x is congruent to minus 1 mod 4, then y square is congruent to x cube minus 1. Y square is congruent to this is that last final expression in the previous step. So y square is congruent to x cube minus 1 mod 4 is not correct. You will not get that. It cannot be satisfied. That means you will not get that if any one of this situation occur. In the proof of the above claim, so this is the new claim. To prove the above claim, we have to consider the following 4 cases. Here we consider the following cases. 4 cases. The first case is that we previously we have 2 situations based on y, and now we have 2 situations, that is x is even, or x is congruent to minus 1 mod 4, and these 2 situations. So properly combining these 2 and 2 4 situations, you get the 4 cases. For 4 cases, and the first case we have y square is we consider y square is congruent to 0 mod 4, and then case and also we take that x is even. See, suppose x is even additionally. So these 2, on y we apply one condition, and on x we apply one condition. If x is even, then x cube is if x is even, then x cube is congruent to 0 mod 4. When y square, and also we have y square is congruent to 0 mod 4, and therefore x cube, thus we get x cube. Then using these 2, when x is even, clearly x cube is congruent to 0 mod 4. And then combining the 2, we get that x cube into then we have x cube is congruent to y square mod 4. Okay, combining these 2 equations, congruence equations, we can write that x cube is congruent to y square mod 4. If the above statement is true, now we consider this statement, the statement that y square is congruent to x cube minus 1 mod 4. So if this is true, then you cannot say that one, the newly derived statement is true. You cannot say that. See, these 2 statements cannot go together, because here we have considering the situation here in the first case. In the first case, we have derived that x cube. We have shown that x cube is congruent to y square mod 4. But there you can give a number here to this expression. Suppose this is 3, the step 3. Okay, in step 3 we have y square is congruent to x cube minus 1 mod 4. This step 3 and the current situation, that is x cube is congruent to y square mod 4, cannot be true. because there here we have just subtracted 1 from the from the right side, or from one side we have subtracted only 1, and that you can show that these two statements cannot be true together. So in the above statement, so if the above statement is true, therefore only one of the statement can be true. If y square is congruent to x cube minus 1 mod 4 is true, then this cannot be true. X cube is congruent to y square mod 4 cannot be true. On the other hand, if this statement is true, if x cube is congruent to y square mod 4 is true, then this statement cannot be true. But you know, we have accepted that okay. Okay, then yes, how do we get that? Here we assume that there exists integer solution. Okay, we have derived this situation. We have derived this situation based on the assumption that there exists integer solution. Okay. Okay, then we consider the first situation, and that when we consider that first situation or first case, then we get the contradiction for the existence of this expression. Yeah, this is the expression that we have derived, and actually this is what we get here. We get this x cube is congruent to y square mod 4, and that actually contradicts the existence of this statement. Next we consider, so in a similar way we have to show that that the statement is contradicted. The existence of that statement is contradicted in all the other remaining cases. So next case is x is congruent to minus 1 mod 4, and y, the condition about y will remain. Yeah, this condition will remain. Y square is congruent to 0 mod 4, and also we change the condition on x, that is x is congruent to minus 1 mod 4. Then you know, you can repeat, you can take three similar statements, x is congruent to minus 1 mod 4, 3 times you can take, and you can multiply these three statements to obtain that x cube is congruent to minus 1 mod 4. After obtaining that, you can rearrange to obtain x cube plus 1 is congruent to 0 mod 4. And then we also have the condition y that remains, y square is congruent to 0 mod 4. Therefore adding these two statements, adding x cube plus 1 is congruent to 0 mod 4 and y square is congruent to 0 mod 4, we get that x cube plus 1 plus y square is congruent to 0 mod 4, that is y square is congruent to minus x cube minus 1 mod 4. That means you can okay, then okay, we also assume that so this is the statement we obtain, the congruent statement that we obtain in the second case, in the case 1.2. Previous case is 1.1. In the case 1, as a consequence of 1.2, case 1.2, we get this. We have derived this statement: y square is congruent to minus x cube minus 1 mod 4. But if the statement y square is congruent to x cube minus 1 mod 4 is true, if that is true, then you know you can directly connect the right hand sides, and you get that minus x cube minus 1 is minus x cube minus 1 minus x cube minus 1 is congruent to the right hand side of this statement, that is x cube is congruent to x cube minus 1 mod 4. That means minus 1 can be cancelled on both sides, and you get that 2 into x cube is congruent to 0 mod 4. 2 into x cube is congruent to 0 mod 4. When 2 into x cube is congruent to 0 mod 4, but you know that contradicts the fact that this is contradicting the fact that x is congruent to minus 1 mod 4. So this statement contradicts the fact that x is congruent to minus 1 mod 4, that we have our derivation in the current case, in the case 1.2 is mainly based on the assumption that x is congruent to minus 1 mod 4. So that statement is contradicted. Therefore which one we have to correct? You have to correct that the the wrong step that we have taken may be that the assumption that y square is congruent to x cube minus 1 mod 4 may be corrected, may be wrong. So this is the problem. Since we have accepted that y square is congruent, since we have used here y square is congruent to x cube minus 1 mod 4 as true, as a true statement, here is the wrong step that we have taken. Therefore in this case also we got the contradiction. Next situation, next case, mainly the second case, the case 2, that in that case we accept the common condition on y, that is y square is congruent to 1 mod 4. We accept that y square is congruent to 1 mod 4, and then subcases, we have two subcases based on the conditions on x. The case 2.1, when x is even. So we get that we have the case 2.1 when x is even, and when x is even, then x cube is congruent to 0 mod 4, and therefore and then using this y square is congruent to 1 mod 4. Combining that, we get that y square is congruent to x cube plus 1 mod 4. Then accepting or taking that statement y square is congruent to x cube minus 1 mod 4. Mod 4, that is the statement number 3. Then using the two, combining the two, we get that x cube plus 1. Then we will get that x cube plus 1 is congruent to x cube minus 1 mod 4. That leads to the conclusion that 2 is congruent to 0 mod 4. That's wrong. That's the contradiction. It will give you the statement that 2 is congruent to 0 mod 4. It's a wrong statement. That means you get the contradiction. Therefore in this case also the statement, the acceptance of y square is congruent to x cube minus 1 mod 4 is contradicted. Okay, the next case, the last case is case 2.2. In that case, y, the condition y is the same, y square is congruent to 1 mod 4, that is that remains, but condition x changes to the second condition, that is x is congruent to minus 1 mod 4. When x is congruent to minus 1 mod 4, you can write as in the previous case, in that is in case 1.2. Just as in case 1.2, you can write that x cube is congruent to minus 1 mod 4. That is x cube plus 1 is congruent to 0 mod 4, and also y square is congruent to 1 mod 4. Therefore y square minus 1 is congruent to 0 mod 4. Minus 1 is taken to left side, and therefore y square minus 1 is congruent to x cube plus 1 mod 4. That is y square is congruent to x cube plus 2 mod 4. Y square is congruent to x cube plus 2 mod 4. Then thus in this case also we get the contradiction. It's because that this statement, if this statement is true, y square is congruent to x cube minus 1 mod 4 is not true. It contradicts. So the statement that we have obtained last here, our last statement, if it is true, then that will contradict the truth value, the truthness of the statement y square is congruent to x cube minus 1 mod 4. Thus in all the four cases we get the contradiction to the existence of the statement that y square is congruent to x cube minus 1 mod 4. Okay, that means y square is not congruent to, we get that y square is not congruent to x cube minus 1 mod 4. It's because we have discussed all the possible situations. Since we have discussed all the possible situations based on the values of x and y, so there is no way to go further to assume that or to show that y square is congruent to x cube minus 1 mod 4. And therefore we now correct that y square is congruent to y square is not congruent to x cube minus 1 mod 4. So and therefore we get the final contradiction, the last contradiction. Okay, there remains some more to do now. So thus when we take the value of x as x is even or x is congruent to minus 1 mod 4, this we get the contradiction, clear contradiction to the existence of the statement y square is congruent to x cube minus 1 mod 4. Okay, then we have so we can proceed only by taking, you can see that one more case is remaining. We have not, as we have discussed the 4 cases, you can see that it's a mistake that I made here. All the cases, all the situations have not been discussed here. Then one more situation is there, and that is based on, that situation remains based on the value of x, that is x is congruent to 1 mod 4 is also possible. See, that situation there remains. We have to discuss the situation further. X is congruent to 1 mod 4. Based on x, we have the situations. It's because we at this moment we need an explanation is very relevant on the basis of x, on the basis of the value of x selected. If x is an integer, and then the 3 situations are possible, which are explained here. Then x can either be even number, or x can be written in the form 4n plus 1. That integer can be written in the form 4n plus 1. If x is not an even number, then it is an odd number. If x is an odd number, then that can be, every odd number can be written either in the form 4n plus 1 or in the form 4n minus 1. Thus we have 3 situations to discuss. Now we have covered the situations x is even, that situation we have discussed, and x is congruent to minus 1. See, x is congruent to minus 1 mod 4. That situation is also discussed. That is, the third situation is also discussed. We have completed the discussion on that. So one more situation is here remaining, that is x is congruent to plus 1 mod 4. That is the situation, x is congruent to plus 1 mod 4. And on this situation we have to proceed further. So if x is congruent to 1 mod 4, then can we consider, and we take the constant k. Let's consider the constant k equal to 4n, and since x is equal to then in that case we can take x is equal to 4n, then if x is congruent to 1 mod 4, then we have, then we can substitute x is equal to what we get then. Okay, since we have discussed this first and the last case, see, we have x is equal to 4n plus 1 actually. Then we can since we can substitute x is equal to 4n plus 1 instead of minus 1. Let's see what is going to happen. It's a mistake. So then k is equal to 4n so again we want to go to the beginning of the result. Oh, this is this is not a substitution actually. We, since the number k, since k is equal to 4n minus 1 the whole cube, 4n minus 1 whole cube minus 4m square minus 4m square. Okay, so this is, as we can take that it is not a substitution for x. So that was a mistake. So since we consider, we consider the number k equal to 4n minus 1 cube minus 4m square. Okay, therefore we are still we have to apply that the effect of x is congruent to 1 mod 4 in this expression, but we will do that later. Now in this expression we can replace, we substitute a is equal to 4n minus 1. So we have that we can replace 4n minus 1 by the number a. and then we get that k equal to a cube minus 4m square. Okay, and that is then k equal to a cube minus 4m square, and therefore we can write that expression then becomes okay, then we consider that y square equal to that different equation we consider. Okay, this is happening in k equal to a cube minus in k we substitute a 4n minus 1 equal to a, then k equal to a cube minus 4m square. Then you can see that when we consider the different equation y square equal to x cube plus k, you can see that when you can replace we replace k by that quantity by k, and then you get that x cube plus a square x cube plus a cube minus 4m square, and now you can rearrange that and write y square plus 4m square can be taken together, and this negative quantity is taken to the left side, and we get y square plus 4m square equal to x cube plus a cube, and that x cube plus a cube can be factorized and written as x plus a into x square minus x into a plus a square. So x cube plus a square a cube will be factorized and can be written x plus a into x square minus x a plus a square. Since we have x is congruent to 1 mod 4, now we are now able to write apply that. We are now going to apply that x the condition or the nature of x. In this case, x is congruent to 1 mod 4, that property can be applied. X is congruent to mod 4, and therefore and also see here a is congruent to, since it is substituted that since we take a is equal to 4n minus 1, therefore a is congruent to minus 1 mod 4. So we have this a is congruent to minus 1 mod 4 coming from this this fact and this expression a equal to 4n minus 1, and therefore combining we can combine that. Then x square is therefore congruent to 1 mod 4. See, we take once again another copy of the same x is congruent to 1 mod 4, the expression, and we get that x square is congruent to 1 mod 4. After that, considering thus we have this expression, we have x square is congruent to 1 mod 4. Then a into x can be you can multiply a these two congruences can be multiplied and obtain that x into a is congruent to minus 1 mod 4. So okay, that is given here. We have x is congruent to 1 mod 4 and a into x minus a into x by multiplying this congruence equation, and that the a is congruent to minus 1 mod 4, that equation can be multiplied to obtain that minus ax is congruent to minus a. Minus ax is congruent to okay, this is not done. This is obtained by multiplying both sides by minus a. Okay, okay, that's a wrong step here. Okay, you can multiply both sides by, it's because a is congruent to, since a is congruent to minus 1 mod 4. Using this fact, you can multiply, since a is congruent to minus 1 mod 4, that means a is not divisible by 4. A is not divisible by 4, and a is not divisible by 4, so you can multiply both sides of that first congruence, x is congruent to 1 minus 1 mod 4 by minus a. Both sides can be multiplied, then we get that minus ax is congruent to minus a mod 4. And the second one, a square is congruent to a square. A square is congruent to a square, that's also correct. A square is congruent to a square mod 4. Then you can add the three, all the three, and get that x square. Sorry, x square is not. Yeah, x square is there. That congruence is here. X square is congruent to 1 mod 4. Then adding x square, then minus ax. this congruence, and then the congruence a square is congruent to a square mod 4. Adding the three congruences, we get that x square minus ax plus a square is congruent to 1 minus a then plus a square mod 4. Okay, but 1 minus a plus a square can be 1 minus a plus a square. How can you combine that? 1 minus a, and that is written congruent to minus 1 mod 4. How can we write that? Okay, that you can okay, here 1 minus see here, that derivation is given here. Here we can see after obtaining 1 minus a plus a square mod 4, and you can write that it is congruent to minus 1 mod 4, and that step is explained here. Since a is congruent to minus 1, a is congruent to minus 1 mod 4, so a square is congruent to 1 mod 4. So okay, then here we get, from the first we get minus a is congruent to 1 mod 4, minus a is congruent to 1 mod 4, and 1 is congruent to 1 mod 4. That statement is also correct. 1 is congruent to 1 minus 1 mod 4. Therefore adding 1, then and this congruence first, then you can add this congruence, and then minus a is congruent to 1 mod 4, and you can add a square is congruent to. So you can add the second, third, and the fourth congruences. By adding second, third, and fourth congruences in the set of the congruences, set of same congruences available here, you get that 1 minus a plus a square is congruent to 1 plus 1 plus 1, that is 3 mod 4. 1 plus 1 plus 1, right side sum is 3 mod 4, but 3 mod 4 can be written as minus 1 mod 4. Okay, since this is congruent to since 3 is congruent to minus 1 mod 4, we get that 1 minus a plus a square is congruent to minus 1 mod 4. So that fact can be is used here. Since 1 minus a plus a square is congruent to mod 4, you can replace that by it is congruent to minus 1 mod 4. Okay, clear. Then clearly this statement says that this congruence says that x square minus ax plus a square is an odd number, and due to this congruence, since this quantity is congruent to minus 1 mod 4, in this statement says that the last statement obtains states that x square minus x, the quantity x square minus x plus a square, is an odd number. Then consider all prime factors of we consider all prime factors of x square minus x plus a square. Next, further we have to proceed more steps. Next we consider all prime factors of the number x square minus ax plus a square. All cannot be congruent to 1 mod 4. When we consider the prime factors of the number, you can say that all those prime factors cannot be together congruent to 1 mod 4. What happens that for that, and this is a claim, this is a new claim. Okay, we claim that if we consider the prime factors of it's an odd number, we have proved that due to this statement obtained, we get that this is an odd number. And then when we think about that odd number, you can consider the prime factors of it's an odd number, and therefore prime factors can be there. It can be divided and can be expressed as the product of prime factors, but all the prime numbers will be odd numbers, because that number is the whole number is an odd number. And therefore and you can see that you can say that all of these numbers cannot be congruent to 1 mod 4, and we are going to prove this claim. And let us take x square minus ax plus a square equal p1 into p2 into etc. to pr, and then all are odd numbers. That's clear. And suppose that all pi's are congruent to Yeah, we want to show that all these prime numbers cannot be odd prime numbers cannot be together congruent to 1 mod 4. You just suppose that all of these numbers, all these pi's are congruent to 1 mod 4. That is, p1 is congruent to 1 mod 4, p2 is congruent, you can write p2 is congruent to 1 mod 4, etc. In similar way, you can write for all prime numbers, that is pr is congruent to 1 mod 4. Okay, then multiplying by multiplying you get that p1 into p2 into etc. to pr is congruent to 1 by multiplying all the congruence equations. The product p1 p2 etc. to pr is congruent to 1 mod 4, and that implies that since this product is equal to the quantity x square minus ax plus a square, you get that x square minus ax plus a square is congruent to 1 mod 4 we get. But the quantity, once again referring the last expression above, which is obtained, we get that x square minus ax plus x square minus ax plus a square is congruent to minus 1 mod 4. But combining this, and this is accepted, and okay, when we combine this expression with then congruence equation with this equation, you get that clearly you are going to get that 2 is congruent to 0 mod 4. That will be a contradiction. 2 is congruent to 0 mod 4 will be a contradiction. You are going to get a contradiction, and this contradiction says that it contradicts the fact that x square is x square minus ax plus a square is congruent to minus 1 mod 4. Okay, therefore you have to assume that at least one pi is congruent to minus 1 mod 4. See, at least some of the some pi will be then congruent to minus 1 mod 4. Okay, for that pi, and then we take that prime number. That prime number can be taken, say suppose p is that prime number having that special property. We take that prime number, then p will be congruent to minus 1 mod 4, and so p can divide. P is congruent to minus 1 mod 4 means p can and also p can divide. P can, since p is a factor of that number, then p can divide x square minus ax plus a square, and also it has this property, and therefore that means p can divide x minus ax. See, x square minus ax plus a square. P can divide, there is a mistake, x square is there, x square minus ax plus a square, that means it can divide the equivalent quantity y square plus 4, y square plus 4m square. Let's check that. What is y square plus 4m square? Where do we get that? We have in the in somewhere above steps we have obtained that y square plus it's not there. That is in the here we have y square plus this is that. Okay, this is that step, that 11th step. That is why we have shown that y square plus 4m square equal to x cube plus a cube. That was shown equal to x plus a into x square minus ax plus a square. P is a factor of this quantity. P is a factor of this quantity. That means P can divide the quantity y square plus 4m square. Okay. Coming back, since P can divide, thus P can divide this quantity, therefore y square plus 4m square is congruent to 0 mod P, because P can divide this quantity. Y square plus 4m square is congruent to 0 mod P. That is, y square is congruent to minus 4m square mod P. Okay, by transfer, this is obtained by transferring 4m square to the right side. Okay, then by our hypothesis, by our hypothesis means since it is given that P cannot divide, so since we have accepted as the important main statement of the proof, main statement of the result, that we have assumed that P cannot divide M. Since P cannot divide M, then consider the Legendre symbol. Okay, since then we know we can consider the Legendre symbol minus 4m square bar P. Okay, we have accepted that in the proof throughout the proof of the throughout the proof of this proof of the statement of the theorem, we are proceeding with the assumption that p cannot divide. We know that we have accepted that p cannot divide m. Next we consider the Legendre symbol. Let's consider the Legendre symbol for minus 4m square. Legendre symbol value of the number minus 4m square with respect to p. Consider the Legendre symbol minus 4m square with respect to p. Using that multiplicity property, Legendre symbol value can be written minus 4m square bar p equal to minus 1 bar p into 4 bar p into m square bar p. Okay, that is equal to minus 1 bar p into 2 bar p into 2 bar p into m bar p into m bar p. Okay, but 2 bar p irrespective of the value of 2 bar p, since we take the square, we will get 1 here. Similarly, m bar p maybe minus 1 or plus 1, that doesn't affect the value since we find the square. So we have plus 1 here. The product of the four numbers can be equal to plus 1. So finally the value of the Legendre symbol value of minus 4 m square bar p will depend only on minus 1 bar p. Okay, minus 1 bar p. What is that value? Since p does not divide m, but this is equal to minus 1 bar p. Okay, since p does not divide m, okay, that's because this value is obtained because p does not divide m. We know that since p does not divide m, otherwise what value we will get? That if suppose p divides m, then the Legendre symbol value will be 0. Here we will get, you have to substitute 0 here. As a result, the entire value will become 0. So due to the important fact that p cannot divide m, you will get the Legendre symbol value. You can see that it reduces to minus 1 bar p, and minus 1 bar p equal to minus 1. Minus 1 bar p equal to minus 1. That Legendre symbol value can be obtained. It's because and also you can see what is written here is y square is going to minus 4m square mod p. Okay, therefore okay, this is the value of y bar p into y bar p, and that's y square bar p. See, we obtain that minus 1 bar p equal to minus 1 because p is going to minus 1 mod 4. Okay, p is going to 1 minus p is going to minus 1 mod 4, and that means p is going to 3 mod 4. So referring theorem number 9.4. Okay, we have that result is there already by referring theorem 9.4. By referring theorem 9.4 and using the fact that p is going to minus 1 mod 4, p is going to minus 1 mod 4, that is p is going to 3 mod 4. If p is going to 3 mod 4, then the value, Legendre symbol value will be minus 1. Okay, and also we have a separate derivation here. One way we obtain, proceeding one way, we get that the Legendre symbol value equal to minus 1. That is minus 4m square bar p equal to minus 1. Minus 4m square bar p equal to minus 1 we obtain. But y square is congruent to, since y square is congruent to minus 4 m square mod p, y square is congruent to minus 4 m square mod p. Now applying the periodicity of the Legendre symbol function, applying that periodicity, we can say that we can write that y square bar p with respect to p actually. So y square bar p equal to Legendre symbol y square bar p is equal to the Legendre symbol minus 4 m square bar p. The Legendre symbol minus 4 m square bar p can be determined using an independent way. This is an independent step. Here it's a new step. We have completed a step here, and this is a new step. In this new step, we are trying to find the Legendre symbol value minus 4 m square bar p using a different procedure. And there we know that for that we know that y square is congruent to minus 4 m square. It's congruent to minus 4 m square mod p, and therefore you can write that when you convert it into the Legendre symbol value, y square bar p is equal to, actually this is not congruent to, y square bar p is equal to minus 4 m square bar p. And but this can be then splitted minus y square bar p equal to y bar p into y bar p using that multiplicity, complete multiplicity property, y bar p into y bar p, clearly that value equal to plus 1. Thus you get that minus 4 into m square bar p, the Legendre symbol minus 4 m square bar p equal to plus 1. So using that independent way, we get that the Legendre symbol value minus 4 m square bar p equal to plus 1. But here you have, in the previous step you have proved that minus 4 m square bar p equal to minus 1. It's a contradiction. Thus we get the contradiction in the last step, in the remaining step. With respect to y, we have three cases, but the first two cases, in the first two cases we have derived a contradiction, we have obtained the contradiction, but only one case was remaining with respect to that value of x. That in that case also proceeded mathematically, we have derived the contradiction. Hence we get that for all values of y and for all values of x, we get in all the cases, we have different cases, in all the cases we get the contradiction. Therefore finally you have to conclude that whenever we assume that x, that equation, that given equation, that Diophantine equation has an integer value x and y, finally we end up with a contradiction. So you have to think that, you have to say that that Diophantine equation do not have don't have any integer solution. Okay, that is the end of the proof. Thank you.